In previous lecture, we have discussed total steam turbine working principle and compounding of the steam turbine. So today we have discussed analysis of single stage turbine, single stage impulse turbine. So see a general velocity diagram of impulse turbine we have already seen in previous lectures. So see, this is this is impulse turbines blade mounted on this hub and this rotate in this direction. This is given here. See, rotate in this direction like that. This is blade mounted on this hub. Pressure equalizing hose given here, and axial direction means this is sharp and this is this. So tangential direction like that, this direction. So this is velocity triangle, this is velocity triangle at inlet, this is outlet velocity triangle. This is outlet velocity triangle and this is inlet velocity triangle. In this, you can see V1 is the inlet absolute velocity, VR1 the relative inlet velocity, VF1 velocity of flow, and VW1 velocity of wheel. Same for suffix 2 used for outlet triangle and respective velocities, means V2 is the absolute velocity at outlet, VR2 is the relative velocity at outlet, VF2 is the velocity of flow at outlet, alpha is the outlet steam angle, beta 2 is the vane angles at outlet, like that. This is nozzle angle, beta 1, and this is alpha 1 is a steam angle, like that. Alpha 2 steam angle at outlet. So this is all notification we know already, because same notification we have used in water turbine. Here in this turbine, impulse turbine, VF1 equal to VF2. VF1 equal to VF2 and VR1 equal to VR2. Okay. Because our blade velocity is same, that's why VF1 equal to VF2 and VR1 equal to VR2, because considering no friction losses in this blade. So see here, velocity vector diagram. This is inlet velocity vector diagram. This is nozzle. Steam coming from this nozzle at high velocity, high temperature, and high pressure. So here, this is direction of this steam like that. This is V1 steam velocity, absolute steam velocity. Means your steam coming in this direction. See, after that, at this steam nozzle direction, make alpha 1 angle to horizontal line. Okay, have you understand or not? This is direction of the steam, and alpha 1 makes 2 angle at horizontal line, that is called inlet steam angle, that is called alpha 1. After that, VR1 is a relative velocity. This point marks on base of velocity of U, means blade velocity. This angle is beta 1, we know this is vane angle at inlet. After that, V1 have two components, VF1 and this is VW1. So VF1 is the velocity of flow and VW1 is the velocity of wheel. We know this is complete inlet triangle here. Same, after that, this relative velocity coming and removing like that in this direction. So this is your blade. This steam acting on this force on this blade and removing like that VR2. This is V2 and this is VF2. So all parameter we know. This is VW2, component of V2, horizontal and vertical, component of V2, VF2 and VW2. See here, steam coming from this direction after removing at this point like that in this direction. So this is outlet triangle. Okay. Now combined diagram of these two triangle, inlet triangle and outlet triangle. See here. So u velocity is common. U velocity is same for both triangle. So we have taken a common. So this is, see, this is inlet triangle. From here alpha 1 to like that. And this is outlet triangle. So here only combined velocity u, that's reason we have draw combined diagram. And here VF1 equal to VF2 means this point also same distance from horizontal line from this line to this. Okay. And VR1 equal to VR2. So any doubt, any queries, please ask me in this diagram because very important for solving the problem. So ask me any question regarding this diagram. Any doubt, any queries, please ask me. All of you. Any doubt, any queries, please ask me because this diagram is very important for the solving the problem. On this diagram, we have solved problem because in this diagram, these two triangle, like that inlet and outlet, we have used all trigonometry relation and using trigonometry find out all these parameter and angles. After solving these finding parameters and angle, we have solved the problem. Very important one thing for solving the steam turbine problem. First we solve this or find out all parameters. VR1, VR2, V1, V2, VF2, VF1, alpha 2, alpha 1, beta 2, beta 1. After solving this, finding this parameter, only one formula for finding work done and second formula for finding efficiency. Very simple problem for this steam turbine. So, any doubt, any queries, please ask me. Any doubt, any queries, please ask me. All of you? Kunal, Prasad, Suraj, Mangesh, Nikita, Maheshwari. Any doubt?
No, sir.
Because this diagram is very important. Okay, thank you. So, next, this is our combined diagram and effect of blade friction. In that case, we have considered this diagram for without considering means considering no friction losses. But here we have considered blade friction. So what effect on friction on this our turbine blade? So see only change in relative velocity means in that case relative velocity VR1 at inlet. So relative velocity at outlet VR2 is different. But in first case, we have considered no friction losses, so VR1 equal to VR2. But here, not VR1 not equal to VR2 because we have considered frictions. Means blade friction, blade and steam. In that case, steam flowing through blade surface, or sorry, steam flowing on the blade surface. That friction we are considering then effect of the VR2. So due to effect of blade friction losses, the relative velocity at outlet is reduced than the relative velocity at inlet. See here, outlet relative velocity is to reduced than the relative velocity at inlet, means VR1 greater than the VR2. Therefore, VR2 equal to CB, VR2 equal to CB VR1, corresponding velocity triangle shown in figure. See here, this is your VR2 and this is your VR1. So CB is a corresponding velocity, sorry, friction coefficient VR2 equal to CB VR1. Okay. Now, see here, in steam turbine, we have seen number of stages there. So, for first stage and second stage, see, this is very important also, because up to you have seen only single stage for in water turbine, but steam turbine number of stages there. So velocity triangles also present for number of stages. So this is first triangle, this is second triangle, this is third triangle, this is fourth triangle. So this is first stage. This is second stage. See, first stage means we have consider all things. Same here, first stage. For indirect triangle, all suffix V1, V2, V1, one suffix for all parameter. Now see here, steam coming from nozzle at velocity V1 makes an angle to horizontal line at alpha 1. This is VR1. This is your blade, rotor blade. So steam passes on this blade and removing at velocity VR2. This is your V2 and this is your U. After that, V2 on the stator blade, V2 impacting or flowing or steam flowing through on this surface and removing at velocity V3. Okay, means at the inlet of the rotor, V1 velocity, sorry, VR1 velocity, and at the outlet of the rotor, V2 velocity. Okay. So, inlet of the stator, V2 velocity, and outlet of the V3. So after that, this is rotor blade. So inlet of the rotor blade relative velocity and outlet is also relative velocity. This is number of stages diagram. So very important point to understanding. So which velocity at inlet? Remember this thing at the rotor, inlet velocity is V1. Inlet velocity is V1, outlet velocity V2. In stator, inlet velocity V2, outlet velocity V3. Rotor, inlet velocity VR3, relative velocity and outlet velocity V4. Means rotor inlet velocity is relative velocity, inlet and outlet velocity is relative velocity, and in stator, inlet and outlet velocity is absolute velocity. This thing is remembered. Now, this is second velocity, combined velocity diagram for second stage. We can see here this combined triangle like that. This is your inlet triangle for second stage. This is your outlet triangle for second stage. Any doubt, any queries, please ask me. Now, velocity diagram for an impulse turbine. No, steam coming from the nozzle at velocity v1 impacting on this blade and moving like that this direction and remove as a relative velocity this blade direction of blade inlet velocity diagram, and this is outlet velocity diagram. We have discussed already these parameters and all things. So all parameters we know V1, VR2, VW1, VB, alpha 1, beta 1, all parameter description given here. VB is the linear velocity of moving blade. V1 is the absolute velocity of steam at inlet moving blade. Exit velocity of nozzle. VW1 is a tangential component of entering steam. VW1 also known as velocity of wheel at entrance. So VR1 relative velocity of steam with respect to tip of the blade and inlet, it is the velocity vectorial difference between VB and V1. So VF1 equal to velocity of flow and axial velocity at entrance to moving blade. It is the vertical component of V1. Alpha1 is the angle of nozzle, the angle which entering the steam makes with the moving blade at entrance minus with the tangent of the wheel at entrance. Beta 1 angle which the relative velocity makes with the tangent of the wheel and direction of motion of the blade. It is also known as blade angle at inlet. The above notation stands for inlet triangle V2, VW2, VF2, VR2, alpha 2, beta 2 are the corresponding values at the exit of the moving blades. They stand for outlet triangle. So all parameter already we know. This is a notification given for the steam turbine, impulse steam turbine. Now a working of this impulse steam turbine. So see here the steam jet with absolute velocity V1 impact on the blade at angle of alpha 1 so to the tangent of the blade. The absolute velocity V2 can be considered having two components, tangential component and wheel component. VW1 equal to V1 cos alpha 1 is parallel to direction of rotation of blade. Stand axial or flow component Vf1 equal to V sin alpha 1 is perpendicular to the direction of rotation of blades. The tangential component of the steam jet does work on the blade because it is in the same direction as the motion of the blade. The axial component doesn't work on the blade because it is perpendicular to the direction of motion of the blade. It is responsible for the flow of steam through the turbine. Change of velocity is in the component causes an axial thrust on the rotor. As the blade move with tangential velocity in peripheral direction, the entering steam jet will have relative velocity to the blade. If there is no friction loss at the blade, relative velocity at inlet is equal to relative velocity at outlet. In that case, we are not considering friction, then VR1 equal to VR2. And as the steam glides over the blade without shock, the surface of the blade and inlet must be parallel to the relative velocity VR1. So the moving blade at inlet must be inclined to the tangent of the blade at angle of beta 1. In other words, to avoid shock at the entrance, vector VR1 must be tangential to the blade tip at the entry. Beta 1 must be equal to angle of blade at entrance. The blade is designed on this principle. So see here in this working principle, we know absolute velocity V1 we know absolute velocity v1 and v2 can be considered as having two components, the tangential component called wheel component and vertical component is called flow component. We know already. The tangential component of the steam jet does work on the blade because it is in the same direction as the motion of the blade. The axial component doesn't work on the blade because its perpendicular direction of the motion of blade. It is responsible for flow of the steam through the turbine. Changes of the velocity in this component causes axial thrust on the rotor. Now, as the blade move with tangential velocities perpendicular direction, the entering steam jet will have relative velocity of the blade. If there is no friction losses at the blade, relative velocity at inlet is equal to relative velocity at outlet. So, as the steam glides over the blade without shock, the surface of the blade at inlet must be parallel to velocity, relative velocity VR1. So the moving blade at inlet must be inclined to the tangent of the blade at angle of beta 1. In other words, to avoid shock at the entrance, vector VR1 must be tangential to the blade tip at entry, that is beta 1, must be equal to angle of blade at entrance. The blade is designed on this principle. Any doubt, any queries, please ask me. In this working of the impulse turbine, impulse steam turbine, any doubt, any queries, please ask me. From above analysis, following point are to be noted. No expansion of steam takes place in the moving blade. The blades only deflect steam. This causes change in momentum and consequently force. If the steam has enters and remove the blade without shock, angle beta 1 should be angle of blade at inlet and angle beta 2 should be angle of blade at outlet. This is an essential condition. Since there is no pressure drop in the moving blade, the pressure on the two sides of the blade is equal. Alpha 1 is the outlet angle of the nozzle if the steam has to enter the next nozzle ring without shock, its inlet must be equal to alpha 2. In a simple impulse turbine, the loss at exit is the wheel component at outlet and V2 cos alpha 2 for minimum loss. This quantity should be minimum, that is alpha 2 should be equal to 90 degree. In that case, the turbine discharge axially and it is called axial turbine. Construction of combined velocity diagram, already explained you. So see how to construct combined diagram. So first, draw the horizontal line and cut off AB equal to velocity blade to some suitable scale. See, first we draw this horizontal line like that and mark AB using suitable scale. AB means blade velocity. From 5, draw line BC at angle of alpha 1 draw a line of alpha 1 at angle with AB cut off AB with A as a center and radius equal to AC. Radius equal to AC. Draw an arc mid line through A at D means here from a point take this is distance like that. Joint AC is represent VR1. From A, draw a line AD at an angle of beta 2. From A, draw line at beta 2 with AB with a scale center and radius equal to AC. Draw an arc that meets through A at D such that AC AD or VR1 equal to VR2. Joint BD, it represents velocity at exit scale. From C and D, draw perpendicular to meet AB, produce E and F. Now, to scale EB velocity of wheel entrance, all scale we have given, when the friction is neglected, there will be no fall of steam pressure as it flow over the blade and VR1 equal to VR2. Also, when friction is absent, beta 1 equal to beta 2 and VF1 equal to VF2. Any doubt, any queries, please ask me. Any doubt, any queries, ask me. Once again explain this diagram. See here, combined velocity diagram. To solve problem on turbine conveniently, it's common practice to combine both inlet and outlet velocity triangle on the common base which represent the blade velocity. See, first we draw this horizontal line. Mark A and B using suitable scale. That is called blade velocity. AB is the blade velocity. Now, draw, mark alpha 1 angle and take using suitable scale. That scale we have taken. Mark point C means we know alpha 1 and this V1 velocity, then mark point C and join this point to A. Okay, means this triangle is we know ABC. This triangle is completed. From C, draw perpendicular to horizontal, that is CE. Means first triangle, inlet triangle we know. After that, take a radius AC and center A, mark this curve like that. Okay. And cut mark arc and like that, this arc. Now we know angle alpha 2 or beta 2. So draw this line by alpha 2 BD and cut this arc and mark point D. Same joint A and D and B and D. This is your outlet triangle and draw vertical component on the horizontal line DF. This is your VF2 means total inlet and outlet triangle we have draw here. So all parameter we know by proper scale. Now, effect of blade friction So in an impulse turbine, the relative velocity remains same as the steam passes over the blade. Its friction is neglected. In actual practice, the flow of steam of the blade is registered by friction. The effect of this friction is to reduce the relative velocity of steam while passing over the blades. So generally, there is loss of 10 to 15% in relative velocity owing its friction in blade. VR2 is less than VR1, and we may be right VR2 equal to K VR1 and K equal to VR2 upon VR1. The ratio of VR2 to VR1 is called blade velocity coefficient or coefficient of velocity friction factor K. The effect of blade friction is to reduce relative velocity at outlet and consequently VW2. This is turn wheel causes reduction in the work done and blade efficiency. Depending on the shape of the blade, values of K vary from 0.75 to 0.85. Means here 10 to 15% loss due to frictions. This is coefficient of friction. VR2 equal to K VR1 means K equal to VR2 upon VR1. Now force on blades and work done, power developed by blade. So force on blade and work done by blade. The work done by may be found out from this change of momentum of the steam jet during the flow over the blade. As mentioned earlier, velocity of wheel is responsible for the work of the blade. Force on the rotor. According to Newton's second law of motion, tangential force on the rotor equal to mass into tangential acceleration, means mass into VW1 minus VW2, where mass equal to mass rate of steam flow kg per second. Now, actual VW2 is negative as the steam is discharged in opposite direction to the blade motion. So VW1 and VW2 are added together. Generally, force equal to mass flow rate into VW1 plus or minus VW2 Newton. So positive sign is to be used when VW2 and VB are in opposite direction as the shown above, and negative sign is to be used when the VW2 and VB are in same direction. So power developed by the turbine equal to power equal to rate of doing work. So mass flow rate into V1 plus or minus VW2 into VB watts. This power is known as rim power or diagram power to distinguish it from shaft power. Axial thrust on rotor. Axial thrust FA equal to mass flow rate into Vf1 minus Vf2 Newton. This axial force must be balanced or must be taken by thrust bearing. Now, efficiency of the turbine. Blade or diagram efficiency, it is defined as the ratio of work done on the blade to energy supplied to the blade. This is called diagram efficiency. So V1 is the absolute velocity of steam at inlet unit meter per second. M is the mass of the steam supplied kg per second. Energy of steam supplied to blade 1 up m V1. Work done on the blade, mass flow rate into VW1 plus or minus VW2. diagram of bread efficiency. Bread efficiency equal to work done on the bread or energy supplied of the bread. So work done equal to mass work into VW1 plus VW2 into VB upon energy supplied of the bread equal to 1 half mass work into V1 square. So 2 VB VW1 plus VW2 upon V1 bread velocity. Now see here gross or stage efficiency. Stage consists of set of nozzle and row moving bread, and so stage efficiency include the performance of nozzle also. Stage efficiency is defined as the ratio of work done on the bread per kg of steam to total energy supplied per kg of the steam. If H1 and H2 represent before and after expansion of the steam through the nozzle, then the enthalpy drop H1 and minus H2 is the enthalpy drop of stage. So heat energy H1 minus H2 is the energy supplied per stage per kg of steam. So stage efficiency equal to work done on the bread per kg of steam, total energy supplied per stage per kg of steam. Now efficiency or stage efficiency equal to VW1 VW2 upon VB upon H1 minus H2. Means stage efficiency equal to VW1 plus or minus VW2 VB upon H1 minus H2. This is diagram efficiency 2 times VB VW1 VW2 upon V1 square. This is stage efficiency. It is defined nozzle efficiency. So nozzle efficiency, this is discussed in next lecture. Then any doubt, any queries, please ask me. Next lecture will be continue at 12 a.m. means next lecture at 12 a.m. So all of you requested to present for this lecture after